So in this video we're going to start chapter 13. 13.1 is called sequences. In math, the word sequence is what we use for a list of numbers. The numbers in the list are called the terms of the sequence. We're mainly going to study infinite sequences, lists of numbers that go on and on indefinitely, forever. So here's an example, 10, 20, 30, 40, 50, 60, ... is an infinite sequence. And when we write that ... on the end, that just means that the pattern continues indefinitely. And the pattern should be obvious by that point, or the hope is that we can see the pattern at that point. Sometimes people also talk about finite sequences that come to an end after a certain number of terms. We will focus on infinite sequences in this course. And we're going to use the following notation. So I'll push this up a bit. We're going to write this a sub n, or sometimes people just read this as an, to denote the nth term of a sequence. So on red here on the side, I note you can say a sub n or an for short. When we say the nth term of a sequence, that kind of nth is kind of a weird thing to write down, but it just means we're talking about a notation that represents all possible terms at one time. So let's see where this goes a little further here. In our example up above, our 10, 20, 30, 40, 50, 60, etc. example, a sub 1 is 10, that's the first term. A sub 2, 20 is the second term. A sub 3, 30 is the third term, so we're referring to our example up here. A sub 4 is the fourth term, so on and so forth. Now, sometimes we describe a sequence by giving a formula for the sequence. And the way we do that is we give a formula for the nth term, that a sub n expression. In our example, it's really easy to see how we could do that. We can just write a sub n is equal to 10 times n. And what I just put in the red box there, that kind of sums up that whole sequence from our example. Because from that formula, we can get any term we want by plugging in the corresponding value of n. So for example, if we wanted to know what the 44th term was of that sequence, that would be a sub 44. That's going to be equal to 10 times 44, which I've written down here. Of course, 10 times 44 is 440. So we know the 44th term of that sequence is 440. Okay, let's start doing some exercises now. And it's really a big part of this is just getting used to this notation. There's not a lot of math calculation involved so much. So in exercise 1, we want to write the first four terms of the sequence given by this formula, a sub n equals n minus 1 over n plus 1. So we want a sub 1 would be the first term. And what I'm going to do is if I put 1 in for n in this subscript in a sub n, I'm going to write 1 in for n in the other positions also. So I would have 1 minus 1 over 1 plus 1. Of course, that's 0 over 2, or 0. So a sub 1 is equal to 0. A sub 2. So now in this formula, I'm going to plug in 2 for n. I'll have 2 minus 1 over 2 plus 1. 2 minus 1 is 1 over 3. 1/3 is a sub 2. A sub 3 is going to be 3 minus 1 over 3 plus 1, which is 2/4 or a half. A sub 4 is going to be 4 minus 1 over 4 plus 1. That's 3/5. And so there we got the first first four terms of that sequence. Now, if I wrote those out as like 0's the first term, 1/3's the second, 1/2 is the third, 3/5 is the fourth, and I put my dot, dot, dot on the end, just notice the pattern is not clear just from looking at these terms. So the pattern is not clear if we don't have a formula. Or for this example at least. And that's often going to be the case. The formula is going to be really helpful because without the formula we just wouldn't have any idea of what the actual pattern was. So let's look at exercise 2 here. We're going to write out the first 5 terms of this sequence. A sub n is 1/2 to the n power. So a sub 1 would be 1/2 to the 1, which is 1/2. A sub 2 is 1/2 to the second power, so that's just 1/2 times 1/2, or 1/4. A sub 3 is 1/2 to the third power. 1/2 to the third is 1/8. A sub 4 is 1/2 to the fourth. That's going to be 1/2 times 1/2 times 1/2 times 1/2, 1/16. A sub 5 is 1/2 to the fifth. That's going to be 1/2 to the fifth. That's 1/32. So that's an example where I think it's a lot easier to see what the pattern is just by looking at the numbers. You can kind of see we have these powers of 2 in the denominator. There's something that's called factorial notation that's used in sequences. It's also used in a lot of other areas in math, and we're going to make use of that a bit here. The notation looks like an exclamation mark from just writing sentences, but we don't read it as an exclamation mark. In math, we read it as n factorial. And n factorial means the product of the first n positive integers. So 1 factorial is just 1. 2 factorial is 1 times 2, or 2. 3 factorial is 1 times 2 times 3, turns out to be 6. 4 factorial is 1 times 2 times 3 times 4 is 24. 5 factorial, so what you do is you just start with 1 and you keep multiplying successive positive integers until you get to the number in question. So 1 times 2 times 3 all the way up to times 4 times 5 for 5 factorial. And that product turns out to be 120. And by convention, we say that 0 factorial is equal to 1, and there's really no way to make sense out of this. I've seen YouTube videos trying to explain why, but it really is just a matter of convenience. It makes certain formulas easier to write down. That's why we say 0 factorial is 1. So now let's do another example where we write out a few terms of this sequence. A sub n equals n squared over n factorial. So nothing really hard about this, just getting used to the notation. A sub 1 is 1 squared over 1 factorial. That's 1 over 1, or just 1. A sub 2 is going to be 2 squared over 2 factorial is 4 over that 2 factorial is just 1 times 2 is 2. 4 over 2 is 2. A sub 3 is going to be 3 squared over 3 factorial. That's 9 over 1 times 2 times 3 is 6, or 3/2. A sub 4 is going to be 4 squared over 4 factorial. 4 squared is 16. 4 factorial, we can still see there up at the top of the screen, is 24. So 16 over 24, I think we can reduce that a little bit to 2/3. A sub 5 is going to be 5 squared over 5 factorial, which is 25 over 5 factorial is that 1 times 2 times 3 times 4 times 5, or 120 that we wrote up above. And let's see, we can reduce this a little bit. We can divide by 5 above and below. And I think we're going to get 5/24. So there are the first 5 terms of that sequence. Here's another one where without the formula, I don't think the pattern would be clear at all, right? Like this 1, 2, 3 halves, 2/3, 5/24. I wouldn't be able to guess if I didn't have that formula to work from. Now there's something called the graph of a sequence. And a graph of a sequence can help us understand what's happening to these numbers as we go down the line. It gives us a picture. And we graph a sequence by plotting the points. The x-coordinates are just going to be positive integers, like 1, 2, 3, so on and so forth. The y-coordinates are going to be the sequence values. So a sub 1, a sub 2, a sub 3. So let's go ahead and we're actually going to plot the first 9 terms of this sequence that I think we already calculated a bunch of these for a sub n equals n minus 1 over a plus 1. So the first point we're trying to find is 1a sub 1. So that's 1 comma 0. We already figured out a sub 1. 2a sub 2 is 2. And I'm going back to my exercise 1 here, right? We already had a sub 2 as a third to a third. Then we have 3 comma a sub 3 is 3 1/2 we got. 4a sub 4 is 4. A sub 4 was 3/5. Again, I copied all those from our exercise 1. Now we gotta figure out some more of these. Let's see, just on the side here, a sub 5 is going to be 5 minus 1 over 5 plus 1. So that's going to be 4/6 or 2/3. So 5a sub 5 is 5 2/3. 6a sub 6 is, let's see, a 6 is 6 minus 1 over 6 plus 1. That's 5/7. 6 5/7. 7a 7 is 7a sub 7 is 7 minus 1, 7 plus 1 is 6/8 or 3/4. And 8a sub 8. A sub 8 is 8 minus 1, 8 plus 1, 7/9. And finally 9a sub 9, I think was the 9th one we wanted, is going to be, let's see, I need a sub 9 is 9 minus 1 over 9 plus 1 is 8/10, 4/5 or 0.8. I guess I'll write 4/5. There we go. And now, it's not, again, not hard, but just an exercise in trying to visualize what's going on here now. Now, to plot these points, I already set up a little graph grid here, and I wanted to have room for all my x values because we wanted the first 9. And I actually figured this out ahead of time. I could see that none of these, I don't think any of these y-coordinates are greater than 1. They're all between 0 and 1. So I just set up my y-axis to give me a little bit of spread between 0 and 1, 0.2, 0.4, 0.6, 0.8, and 1.0. And so our first point is 1, 0, so that's right on the x-axis. 2, 1/3, 2 is about 0.3. 3 1/2, 3.5 is exactly between 0.4 and 6. 4 3/5 is 4.6. 5 2/3 is 5.66. 6 6 5/7, right? What's 5/7? I don't know. 5 divided by 7 is about 0.71, so 6.71. 7 is 3/4, so 0.75. Oops, that's not right there. 8 is 7/9, that's 0.77. Okay, so I'm still not to 0.8, huh? Oops, I'm having trouble lining my things up here. 9 is finally 0.8, right? 4/5 is 0.8 exactly. And I guess that's as far as we want to go. So let's do a little magic here, make some of my mistakes disappear. And that's just, again, what do we see here is these points are kind of rising up. And it also seems like they're leveling off. And in fact, that might be a question, like what'll happen when the input value is huge, like a sub 100, a sub 200, a sub 1,000. But for now, we just want to make this observation that we kind of have this pattern of values, and that's the graph of a sequence. Okay, a little bit more.